Okay, so first, an interesting prelude to relativity, which I read recently, was a book called Einstein's Clocks and Poincaré's Maps. And it's a history of timekeeping and map making in the 19th century and their surprising relevance to the theory of relativity, because in relativity, we basically have to come up with very precise definitions for what we mean by time. That might not seem like such an important thing in non-relativistic physics. You just sort of take it for granted that, hey, you time something, you run your stopwatch, you see how far something goes in that time, divide distance by time, boom, you've got a velocity. But in relativity, we wind up thinking more carefully about time. And the prelude to that is that in the late 19th century, when people started using things like telegraphs and trains, precision timekeeping mattered a whole lot. Traditionally, every town had had their own local time. Noon was when the sun was at its peak in the sky, and nobody worried too much about the fact that noon in this city would be slightly different from noon in that city. It was completely irrelevant. But when you need a train schedule, and somebody starts off in this city at whatever time and gets to that city at whatever time, the people in the city that the train left from have their watches set to that local time. They get to a new city. Everybody had better be able to agree on what that arrival time is. Likewise with telegraphs, when people are able to do long distance transactions very quickly, it could be very important to figure out, was that order to wire the money issued before or after a deadline? Did somebody tell you to buy this stock before or after some news was announced by telegraph? That could matter a whole lot for an insider trading investigation. And so there were all of these business purposes for which precision timing mattered. And that made people start thinking very carefully, what does it really mean to say that this is the time? Okay, what is the procedure by which we are going to decide which standard of time to use? What is the procedure by which we're going to calibrate these clocks, given that it'll take time for information to pass? Map making, measuring distance, surveying is a whole lot more complicated than just running a ruler or tape measure. So defining positions started to matter a whole lot, particularly for global empires that were measuring distance on a curved globe and had to come to very good agreements on exactly who controlled which side of, or who controlled this strategic waterway along what side of what line. And so Einstein and Poincaré both spent a lot of time in their careers prior to relativity thinking about very precise definitions of space and time. Time and distance were not just things that they just kind of looked at on a ruler or a clock. They were products of procedure. And so they were actually very well positioned for the idea that even on a fundamental level, these things might require nuanced definitions. All right, so that's what we're going to be talking about. The other thing I will mention before we start relativity is that I've scheduled a midterm review session. The midterm will be next Friday. We'll do it like we did the previous midterm. It'll be available at 10 a.m. You'll have 2 hours to download it and either print it or do it on a tablet, and one way or another produce a file that has your answers to the questions and upload that file to Blackboard. And so the midterm review session will be next Tuesday at 4 p.m. We'll go about an hour, hour and a half. I'll take questions on last semester's midterm. I'll take questions on the homework. Any questions on the midterm or the homework or anything else related to the optics that we were doing before, the stuff we were doing before we started relativity? Okay, hearing none, let's start relativity. Now, Relativity requires a rewiring of your intuition. So we're going to move slowly. Today we're just going to talk about background. We're going to talk about some history. We're going to talk about precise definitions of reference frames and go to Galileo. Then next Monday we will gradually build up to the central paradox of relativity, and then we will start defining time and ways of measuring and calculating time. So let's start with some myths about relativity. First of all, in the 90s, during what was called the science wars, it was very popular for sociologists and philosophers to say that all of reality is like subjective, man, and like Einstein proved that, you know, everything is just subject to your perspective, man. So like everything is like, you know, valid within a certain cultural reference frame. I'm not going to get into subjective versus objective morality here. I'll just note that calling everything subjective seems to be very popular today, with some people feeling like they can call anything they don't like fake news. But Einstein certainly didn't prove that things were subjective, even though Einstein did prove that people moving at different rates relative to each other might measure the time between two events to be different. He also proved that there were very precise mathematical relationships. If I run a stopwatch and measure the time between when a spaceship takes off and when I see it explode, and you, traveling relative to that spaceship, run your own stopwatch and measure your own time between those two events, we might not agree on them, but there will be a precise mathematical relationship between my measurements and yours. I can use certain equations to figure out exactly what you must have measured. And then I can go and talk to you and ask you, and if you did your measurements carefully and I did mine carefully, we will discover that, yes, this mathematical relationship holds. Another popular myth about Einstein is that he failed at math. There's no evidence for that. I've read many biographies of Einstein. Many of those biographers have gone to Europe and searched through old family records and everything. And while I don't think anybody has gone to every single school district office and looked through their old archives and dug up every old report card, no one's ever found any evidence, not even a letter from one relative to another saying, oh, little Albert is doing so terribly in school. The motive for this seems to be that people want to say, hey, Einstein was bad at math, and Dr. Small says, I'm bad at math, so that means I'm like Einstein. No, that's not what it means. Not at all. Not every bad math student is Albert Einstein. I mean, Adolf Hitler was bad at art, but no one goes around saying that if someone makes a bad painting, they're going to plunge the entire world into war and kill millions of people. So being bad at math does not make someone an Albert Einstein. The only evidence we ever have of poor math performance by Einstein is that in college, he went through a phase where he spent more time in coffee shops than in class, and apparently one of his math professors was underwhelmed by this guy who never showed up or did homework. Okay, you might say that this is why math professors need to be less judgmental. All I'll say is that yes, there are plenty of people who failed math. Most of them will not turn into Einstein. Many of them will still do fine in life, not because their poor performance in math was a harbinger of some hidden genius, but simply because at some point they decide that they should spend less time hanging out in coffee shops and more time doing what they need to do. And lo and behold, when they do what they need to do, it works out. Another myth about Einstein is that he worked in the patent office because the world didn't appreciate his genius. Well, his early academic career was complicated. Certainly he did have some problems with some professors, but working in the patent office is hardly a form of exile or a judgment that one has failed. In fact, working in the patent office is actually a really good job. There's a lot of science majors who enjoy working in patent offices because it's not just a matter of filing some paperwork. You're taking a patent application, which is a detailed description of a piece of technology, you're evaluating it and figuring out, does this piece of technology that they describe differ substantially from other technology that people have previously filed patents for, which means you need to know about that technology. You need to know about the other patents. It's actually a job that requires a lot of technical skill. Patent offices hire lawyers, but they also hire a lot of scientists. And it's not for everyone. Some people don't enjoy that kind of work, but some people really do. Honestly, it wouldn't be the worst thing in the world to think about working in the private sector for a few years, gaining some skill and appreciation for a certain area of technology, gaining some real experience in it, and then either getting a job at the US Patent Office or getting a job at a law firm that handles patent cases. Often law firms will actually hire scientists who have some experience in the private sector, put them to work on patent applications, and then pay for them to go to law school. So Einstein actually had a really good job. Obviously, it wasn't the job that he was best at. The job that he was best at was revolutionizing physics. But he actually got one of the better jobs that a science graduate could get, and you would do well to think about that job. A more controversial, understandable claim about Einstein is that his first wife, Mileva Maric, was, or Maric, I'm not sure how it's pronounced, was a major contributor to the theory of relativity. The background to that, here's what we do know. We know that his first wife, whom he met in college, was a physics major. She was apparently pretty smart. And so it's entirely possible that the two of them did have some stimulating conversations, that she did help him formulate the theory. It's possible. The two main pieces of evidence that people cite for her role is that at some point in a letter, he wrote that we, meaning he and his wife, are working on something. Now that could mean anything from she's developed a substantial portion of the theory to she has supported him through the work, like many spouses do for their spouse's career. The other piece of evidence is that he agreed to give her the money from his Nobel Prize. Now, on the Nobel Prize, keep in mind that they had been wanting to get divorced for a while, and she agreed that she would give him a divorce if he gave her the money from the Nobel Prize. Basically, that would be in lieu of alimony. That would set her up because she hadn't worked in years. Women weren't allowed to really have careers back then. This would set her up. This would compensate her for the time she spent supporting him in his career. This would enable her to provide for the children. And back then, you had to have an agreement on a divorce. Today, divorce is much easier. Back then, divorce was harder to get. The other thing, and this is not putting her down, this is putting him down. Everybody wants to hypothesize that he spent a lot of time talking physics with her. The problem, and this is something very bad about him, is that if you look at the historical record, there's not a whole lot of evidence that he spent time talking to his wife about anything. There's considerable evidence that he spent a whole lot of time talking to other women, to put it mildly. That's part of why that's a big part of why they got divorced. Einstein may be a scientific hero, but as a hero of morality and family life, no, he was not a hero in those realms. So all that we can say for sure about Mileva Maric is that the society that she lived in denied her the opportunity to pursue a career in physics. That's an injustice on its own. I think that's a big enough injustice against her and everyone else in her time that alone is worth lamenting. Did she contribute to the theory of relativity? I don't think we'll ever know for sure. Moving on with Einstein and morality, some people say that Einstein bears the credit or the blame for nuclear bombs. E equals mc squared is only a small part of the physics behind nuclear bombs. Most of the physics behind nuclear bombs involves a whole lot of other things. The biggest role that Einstein played in the nuclear bomb is that in the early 1940s, the physics community realized that it would be possible to build a nuclear bomb. They wanted to inform the government, But as you can imagine, with a world war breaking out, the government was rather busy. It was hard to get the attention of people high up. If some random person goes to the president or the secretary of defense and says, hey, I have an idea for a super weapon, well, you know, that you're not going to get very far. So some physicists who knew more nuclear physics than Einstein did came to him, explained the situation, and he agreed to sign a letter which was sent to Franklin Roosevelt. And this letter resulted in the government initiating the Manhattan Project, which built the nuclear bomb. That was his contribution. It's interesting because many claim that Einstein was a pacifist. Einstein was pretty strongly anti-war for most of his life. He was adamantly opposed to World War I. Around World War II, though, like a great many other people, he looked at the fact that the world was threatened by a dictator who wanted to murder every Jew in existence, looked at his own last name, realized, this might be a problem, and he, like many other physicists, decided that maybe absolute pacifism was not a tenable position. And given that some of Germany's best scientists, the ones who stayed, were apparently working on a nuclear bomb, he decided that he would rather that the nuclear bomb be used by the United States than by Adolf Hitler, and who can blame him? Finally, there's a whole lot of Einstein quotes out there. Don't believe most of them. I mean, in 1946, Einstein said that 90% of the quotes on the internet are false. So keep that in mind. All right, a little more serious history here. Relativity goes back to Galileo. In 1632, Galileo wanted to answer one big and seemingly quite important objection to the heliocentric model. If the Earth's moving so fast, why don't we feel it? I mean, if you're riding on a horse, you feel it. If you're riding on a wagon, you feel it. You feel the wind. It's hard to sit steady on a moving vehicle because moving vehicles in practice are always shaking, especially back then. So Galileo came up with the ship thought experiment. Imagine you've got someone in their quarters below deck, and the ship is moving as steadily as any ship could move in 1632. And you let go of an object, and it'll fall to your feet. Even if the ship is moving fast, the object falls to your feet. Likewise, if you're at the top of the mast, that's this thing up here at the top of the sail, and you drop something, it falls directly to the deck. Whereas if the ship were racing ahead and the thing were falling down straight relative to the ground, you would expect the thing to fall down, but the ship goes this way, and by the time the thing gets down, maybe the ship has already outrun it and it falls into the water. Of course, that doesn't happen. And so Galileo's conclusion was that we can only detect relative motion. If I'm inside the ship and I let go of something, event one, the thing is already moving with a horizontal velocity, which is equal to my velocity and the velocity of the ship. It acquires a vertical velocity. And so if somebody standing on shore is watching it, if there was a window in this little cabin here, that person on shore would see the object that I let go of go both to the right and down. So it'd have a diagonal velocity, except it would really be a parabolic path. So Galileo concluded that we can only see relative motion. That's why we don't notice the motion of the Earth. We're moving with it. 50 years later, Newton agrees with Galileo, but says that we can detect absolute acceleration, but only spinning absolute acceleration. Because if you take a bucket of water and you spin it, or you take a bowl, you could do this after class. You could take a bowl, put water in it, start spinning the bowl, and the water will rise up on the sides of the bowl. And that's how you can tell that the bowl is spinning, that the water is accelerating. But this is circular acceleration. He conceded that we can't detect absolute linear acceleration. Think about a train car. If it's going at constant velocity and you're hanging on to something by a string, well, the string hangs straight down. You can actually learn a lot of relativity from riding trains. And every time I teach relativity, I vow to myself that I'm going to organize a field trip on a metro rail train. And I never do it. And this year I have a good excuse for not doing it, but that's what I always vow, and I never do it. I actually lived in the DC suburbs for 2 years, working at a federal research institute. I took the subway to work every day. And when the subway train is going at constant velocity, everything feels normal. But when the train is speeding up or slowing down, then you feel, if it's slowing down, you feel like you're lunging forward because the seat below you is racing backward relative to you. And likewise, when the train speeds up, you get thrown backward, just like in a car. So when the train is accelerating forward, if you were to hang on to something by a string, it would get thrown back, the string would hang diagonally backwards. But imagine that instead of the train racing forward, accelerating forward, imagine the train was sitting on an incline or moving at constant velocity on an incline. The string would hang down again because gravity is down and the floor is actually diagonal. And of course, an outside observer can say, hey, in the first case, this train is speeding up. I'm standing here on the ground, I'm watching the train car, I see it speed up. In the second case, they see that the train car is on a hill, and they see that underneath that train car, there is a giant rock with a radius of several thousand kilometers, and it's exerting a gravitational force. But within the train car, nobody knows whether they're accelerating forward or they're on a hill. You might say, well, of course they know. Well, they know only because they look out a window and they see what's going on, or because the conductor says, hey, just so you know, we're putting on the brakes. But if all you were to do was physics experiments within a closed box, you don't look out the window, you don't ask the conductor anything, you just sit there in your train car doing physics experiments with things moving or strings hanging at angles, all the results you would get in this case are the same as the results you would get in this case. And so this equivalence between an accelerating reference frame and an inclined plane and a gravitational field, that's actually really important for the relativistic theory of gravity, which we will only say a little bit more about this semester at the very end. And strangely enough, it turns out to be really important for GPS. GPS wouldn't work unless we understood the equivalence between gravity and accelerating reference frames. All right, so for a while people thought that that's how relative motion works. You can't detect absolute velocity, only relative velocity. Can't detect absolute linear acceleration, only relative acceleration or circular acceleration. And that's where things stood. And then in 1862, Maxwell calculated the speed of light. And he didn't calculate the speed relative to the Earth or relative to the sun or relative to his lab or relative to some high maintenance relative or coworker that the world revolves around. They just calculated the speed of light, okay? Maxwell just said, here's the speed of light. The big question was relative to what? Because there was no other object in his calculations. So everybody just assumed that this must be relative to the ether, to some mysterious fluid that fills space but is completely undetectable. And this bothered people. So in 1887, Albert Michelson and his collaborator Morley looked for absolute motion of light. Michelson was the father of American physics. He was the second president of the American Physical Society. He was the founder of some very important physics departments. He was the founder of really federally funded physics research in that he did some very important experiments at the US Naval Academy where he was a professor. There's an interesting story. He came to the US as an immigrant. His family opened up a store in Nevada during the silver rush. They decided that rather than mining for silver themselves, they would just sell things to all of the people who were mining for silver. It was actually a pretty good idea. He wanted to attend the US Naval Academy, so he got on a train, went to DC, went to the White House, knocked on the door, got an appointment with the president. This is something you could do in the 1870s. asked to be admitted to the U.S. Naval Academy, got in, graduated, served on a ship for a few years, then became a professor at the Naval Academy, did high precision measurements of the speed of light, then went to Europe, worked on a PhD. Back in those days, you could be a professor without a PhD. Got discharged from the Navy, served as a professor at a number of U.S. universities in their early days. Those universities are still around. Case Western, University of Chicago, Clark University. Case Western and Chicago are pretty famous schools today. Clark is a little more mid-tier, but still, he was the father of physics at many institutions. And the students who he trained then trained other students. And you can go through the lineage of who studied with who, and the vast majority of American physicists, myself included, can trace our lineage to Michelson. Anyway, here's Michelson's theory. All right. Light must be moving relative to the ether. So if the Earth is moving through the ether, then the speed of light relative to someone on Earth would be c minus the velocity of the Earth. All right? And so if we were to look at light bouncing back and forth inside a cavity, the round trip time would be, well, for at rest with respect to the ether, the distance will be lambda over 2. So lambda over 2 divided by c plus lambda over 2 divided by c equals lambda over c equals the period. And from the period, you could get the frequency c over 2L. But what if the first half of the trip is at c plus the velocity of the Earth, and the second half is at c minus the velocity of the Earth? Because on the first half, the light is going this way, okay? So the Earth is going that way, the light is going that way. So relative to each other, the light is, the speed is even higher. And then the second half of the trip, the cavity moving with the Earth is moving in the same direction as the light. So the velocity of the light relative to the cavity is c minus VE. So you get L over c plus VE plus L over c minus VE. And if you go through all of the algebra, here's the thing. You get a prediction for the frequency where one term is exactly what we got on the previous page, if the cavity is stationary with respect to the ether. And the other term is something proportional to the square of the Earth's velocity. Now, this is a complicated measurement to do. We need to account for the rotation of the Earth. We need to account for the fact that we don't know if the ether is moving. If so, what direction? The direction of the Earth's velocity changes throughout the year. So you're going to have to do a whole bunch of measurements at different times of the year. And Michelson did all of that, and he did it very well. And he won a Nobel Prize for it. And he never detected any ether drift. So that was a mystery. You know, the Earth is clearly moving, but we can't, which means if there's an ether, the Earth must be moving relative to the ether. You could say, well, what if the velocity of the Earth is the same as the velocity of the ether? Well, at one time of year it might be, but then at another time of year, remember, the Earth is going in a circle. So if the ether is going this way, then let's see, am I visible on camera? I just realized I should go to my camera so that I can see what you see. Participants, my camera's on, but now I'm looking for the view where I see myself. Let's get out of full screen mode. I gotta find in my interface where that view is. I can't see myself on camera right now, but if I go to my other device, okay, in my other device now, so imagine that the ether is going up the direction my finger is pointing. but the Earth is going in a circle. So at one time in the year, the Earth is going to be going upwards in the direction of the ether. But then as the year goes on, at some point it's going to be going down opposite the direction of the ether. So at some point in the year, there's going to be relative motion between the Earth and the ether. And Michelson never found any evidence for that. All right. Any questions? Anyone? Now, Michelson actually never abandoned the belief in the ether. Michelson actually thought, come on, there's got to be an ether. Michelson actually thought the relativity was too weird to believe. You might say, well, was Michelson considered a crackpot? Was he considered a crazy man? No, Michelson kept wondering. Michelson never said relativity is wrong. Michelson kept looking for exceptions. Michelson always conceded that relativity makes accurate predictions. He kept thinking that there must be some other theory that we just haven't discovered. There must be some other way of explaining this that would be even better. And he kept doing experiments to possibly oh, great. My other device just started acting weird. All right, there. He kept doing other experiments to possibly validate other theories. But when those theories came out wrong, he said, okay, they're wrong. He was never a crackpot. He was a skeptical scientist. He kept testing relativity more and more. And to this day, if you look in Physical Review Letters, the top journal of the physics community, you will regularly see articles where people test the theory of relativity to more and more decimal places. There's a big difference between the crackpots who send you emails saying Einstein was wrong and the people who publish in Physical Review Letters saying, we are looking for evidence to see if Einstein was wrong. The first group is crazy because they already have a conclusion no matter what the evidence says. The second group says, we know that if Einstein is wrong, the difference between what's actually true and what he said must be less than 0.000, however many decimal places, 1%. Those people are doing some of the best science imaginable. Any questions at all? Okay, enough history. Let's start talking about reference frames. So we're going to use the notion of a reference frame a lot. A reference frame is just a bunch of observers who are all at rest with respect to each other. Now, how do we know that they're at rest with respect to each other? Well, they bounce pulses of light or radio waves off of each other and count the round trip time. And if the light always takes the same amount of time to go from me to you and back, for all I know, I'm moving. For all I know, you're moving, but we're not moving with respect to each other. We might both be sitting on the same bus, and you're always in your seat and I'm always in mine. We are in the same reference frame. Now, an inertial reference, oh, by the way, this is how GPS works, basically. You send a radio signal to a few different satellites, count up the time it takes to get to and from, to the satellite and back, and that tells you how far you are from the satellite. If I know how far I am from this satellite and how far I am from that satellite, then I can work out my position on the Earth. Now, an inertial reference frame is one where if we let go of an object and there's no other force acting on it, it will not spontaneously accelerate. So I'm sitting on a bus and I'm holding on to something and I let go of it. Now, of course, it falls to the ground, but falling to the ground has a perfectly logical explanation. We know that there's a force acting on it because we are aware. We looked out the window and we see that there is this giant rock, and this giant rock is exerting an attractive force on it. Likewise, I'm sitting in a hospital and I let go of a piece of iron, and the piece of iron flies towards the MRI. Okay, well, I'm in an inertial reference frame because that piece of iron only accelerated due to a known force. But what if I let go of something and suddenly it accelerates forward, okay? Well, it accelerates forward, it flies forward because the bus is decelerating, okay? Or maybe it flies forward because the bus is on an inclined plane. That's a non-inertial reference frame. There's no apparent force acting on something, and so and yet it flies forward or backward anyway. And you might be saying to me at this point, wait a minute, a second ago you said that if I let go of something and it falls to the ground, well, we know there's a giant rock pulling down on it. Now you're saying that something flies forward, maybe it's on an inclined plane, or maybe the bus is accelerating or decelerating. Anytime I speak of gravity and reference frames, I have to play kind of fast and loose because the right way to speak of gravity and reference frames is really complicated. And that's why we're mostly going to ignore gravity here. All right. Now, fortunately, we can ignore gravitational effects in a lot of relativistic experiments under two circumstances. One, we are only watching for a short period of time. Delta t is much less than c over g. If we're watching for a time delta t much less than c over g, which is the amount of time it would take for, gravity to substantially change the velocity of something and make it comparable to the speed of light. If we're watching for a much shorter time, we can ignore gravity and relativity. Likewise, if we don't need a lot of precision in gravity, then if we don't need a lot of precision in our measurements, then we can ignore gravity. But if we do need high precision, we need many decimal places, and we need many decimal places in GPS, then we have to pay attention to the relativistic nature of gravity. And like I said, we're going to mostly ignore that, although at the end of the semester, we'll get into the details of it. So if we need to take into account gravity, we need something called general relativity, which is Einstein's 1915 theory. It's the theory that includes the effects of gravity and relativity. If we don't need gravity, we can just do special relativity, his 1905 theory, and we're going to mostly do special relativity. So we're going to observe objects whose velocities change, but we will only discuss what inertial observers would measure. So we sometimes think of an inertial reference frame as being a whole bunch of observers and clocks. All right, basically a person who has set up a whole bunch of laboratory equipment, and all these devices are stationary relative to the observer and stationary relative to each other. Okay, and this is really a legacy of Einstein spending a whole lot of time reviewing patents for precision timing, for things relevant to telegraphs and clock calibration, or clock calibration for navigation, all right? And with each clock, there's a detector. It will detect a flash of light. So if event A is that a flash of light goes off, and all of these things are spaced by, let's say, roughly 3 meters, then the time that it's going to take for a flash of light to go from here to here would be 3 meters over 3 times 10 to the 8th meters per second, which is 10 to the minus 8 seconds, or 10 nanoseconds. So if the flash of light happens at point A, at x equals 17 nanoseconds, well, it's going to be light going in all directions. Some of it reaches here, x equals 20 nanoseconds at t equals 3 nanoseconds. And then it'll get here at t equals 13 nanoseconds. It'll get here at t equals 7 nanoseconds. And here at t equals 17 nanoseconds. Now we're going to talk about distance in nanoseconds or microseconds or in space seconds. For the same reason that astronomers always talk about light years. Astronomers almost never talk about how many meters you have to travel to get to another star. They could always do that conversion, but they almost always say that it's however many light years away, a light year being the distance that light travels in a year. We're going to talk about nanoseconds or light nanoseconds. We'll usually leave out the word light. You're just going to have to get it from context. If I say that something is 5 seconds away, that means that light had to travel 5 seconds to get there. This is something that we do a lot in California. We'll say that, oh, that store is about 10 minutes away from here, meaning 10 car minutes. It's the distance that a car would travel in 10 minutes. All right, now the thing is, having this table of times, x equals 30 nanoseconds when t equals 13 nanoseconds, because here's x equals 30, took 3 and then another 10 to get there. With that, we can reconstruct events. And this is actually what people do in a lot of high energy physics experiments detecting subatomic particles. These subatomic particles travel and emit light. These flashes of light are seen in many detectors, and people reconstruct particle trajectories like that all of the time. So that's why it's valid and useful to think about a reference frame in this way, to think about a reference frame as a whole bunch of detectors and clocks stationary with respect to each other. Because at the South Pole, when a neutrino, a type of subatomic particle, is traveling through the ice, and yes, they have giant neutrino detectors at the South Pole because it's an isolated environment and because the ice turns out to be a really good material to embed the detectors in. They will see a neutrino traveling through the ice, producing flashes of light, and they will detect a flash on each detector at a different time, and they will use that to reconstruct the trail of the neutrino. All right, now we're going to talk about usually 2 different reference frames in our experiments, because usually we're going to be trying to figure out, okay, if one person has these measurements, what are the measurements that the other person would have for when and where these events occurred? We're going to talk about, in the terminology of this textbook, the home frame and the other frame. The home frame will be the default frame, and the coordinates of an event will be t and x. And yes, in relativity, people reverse t and x. It's just convention. They just usually, instead of saying x as a function of t, they usually say tx as a way of describing an event. And the other frame, they'll say t prime and x prime. So if you see a problem described as I'm on a train moving to the right, the other frame is almost always moving to the right relative to the home frame. We set it up that way because if something's moving to the right, the velocity is positive, and negative numbers create more opportunities to make mistakes. So we're going to avoid negative numbers. So I'm on a train moving to the right, and a person on that train walks down the aisle of the train at 1 meter per second. Now, that's v prime. That's a quantity that I measure in the other frame. Okay, it's got a prime on it. And I'm saying that in the other frame, the velocity of this person is 1 meter per second. So x prime is just 1 meter per second times t prime, whatever time I measure for how long they're walking, plus x naught prime. You know, I'm over here, they start off over there. So I'm always at my origin. Virtually always, we will say that the observer who defines the other frame, the person that everything in that other frame is measured with respect to, is at x prime equals 0. And the person in the home frame, the person that everything is measured with respect to, is at x equals 0. So x prime equals 0, and x equals 0. And we'll usually also say, you know, if this person in the other frame is moving at constant velocity, at some point they must line up with the observer on the ground. At some point, the person on the train who defines the other frame must line up, must be at the same x coordinate, different y and z coordinates, but same x coordinate as the person on the ground defining the home frame. And we will usually start our watches at that moment. We'll start our clocks when x prime and x are both 0, so that these two observers line up here, t equals t prime equals 0. Now at a later time, the x-coordinate of the person who's on the train, the person who defines everything on the train, well, they got two different x-coordinates. As far as the person on the train is concerned, they're still at x prime equals 0. We're always at our own origin. We never move relative to ourselves. As far as the person on the ground is concerned, that observer on the train is at x equals vt. And the walker is at, well, somewhere relative to that. They're a distance x naught prime plus 1 meter per second t prime to the right. So the observer on the ground says that the x-coordinate of the walker is whatever the x-coordinate of the train observer is, plus these two terms. And they're related, these two different descriptions are related because the person on the train says that x prime walker is 1 meter per second plus times t plus x naught prime. The person on the ground says something else, but they're related by the Galilean transformation, a simple rule which says that x prime equals x minus vt, right? Because if we subtract off vt, and remember that in Galilean physics, everybody agrees on time, so t prime equals t. If I take this big expression here, subtract vt from it, I get back the coordinate of the person on the train, the person walking on the train relative to the person on the train. If I take the coordinate of the observer on the train, well, according to the person on the ground, the observer on the train is at vt. If I subtract vt from that, I get 0, which is what the observer on the train thinks their own coordinates are. Any questions? Anyone? All right, then we're going to go through some questions from the end of the chapter. We're only going to do a few of these in the interest of time, but all of these are the 2-minute problems at the end of the chapter. And normally in class, I would have you vote on them. I think that what I'll just have you do is use the raise hand function on the participant list. It looks like you can see how or on my other device, I can see how that's moving, but okay, there. So on the other device, you can see that there should be a way for you to raise your hand. If you look under the More button, it's going to be different for you than it is for me, but there should be a raise hand button. So here's a list of situations. And for each of them, you want to tell me if it's inertial or non-inertial. And technically, well, we'll get to that. Tell me if it's inertial for everyday purposes. So, A, how many people say that a non-rotating frame floating in deep space is inertial? Raise your hands if you think it is. Well, I say it is, because if we let go of something on that spaceship, it's just going to float. Now, something that's rotating at 1 revolution per hour. That one is a little more subtle, because if it only goes around, it's a It's a spaceship rotating once per hour. That's a pretty slow rotation. It's not like when you're on a ride at an amusement park, and if you let go of something, it goes flying. That's a very slow rotation. What about a non-rotating frame that is stationary relative to the sun? Attached to the sun, if taken literally, would mean burning up. But what if it's just not moving relative to the sun? That one's subtle, because on the one hand, it would certainly seem like an inertial frame, but if we were to watch it for 1,000,000 years, the sun is going around the center of the galaxy. So if we were to watch it for a long enough time to see its velocity change, then we would have to treat it as a non-inertial frame. And so when, say, if somebody's doing a calculation for trajectories in the solar system, you could treat a frame stationary relative to the sun as inertial. But if you were doing a model of the galaxy and you were doing a computational model for hundreds of millions of years, and we go around the center of the galaxy every 200 million years, then that's a rotating frame, because you're watching on a time long enough that things have changed. I want to do one more. The laws of physics are the same in every reference frame. So must an interaction between objects conserve energy in every reference frame? Meaning that if we do an experiment, and we do this on a train car, and one person watches the experiment sitting on the train car, and the other person is on the ground watching the experiment through the window, will they both agree that energy was conserved? How many say true? How many say true for that? It's definitely true. Everyone agrees that energy is conserved. Now, people on the ground are going to measure the kinetic energies of the objects very differently from people on the train, because as far as a person on the ground is concerned, everyone on that train is moving, and possibly moving at very high speed. So people on the ground might disagree about what the kinetic energy was before the experiment was done, before the objects changed. You know, maybe we did a chemical reaction which caused an explosion and made things move. We might disagree on the kinetic energy before. We might disagree on the kinetic energy after. The one thing we would agree on is that the change in kinetic energy was equal to the amount of energy released from that chemical reaction or whatever. At this point, it's 10:52, so I'm going to stop here. I am going to post all of these questions from the end of the chapter, even though you have the questions in the book. My slides here include the answers. So have a good weekend. As always, if you have questions on homework or anything, you can email me. And I hope you have as good of an Easter weekend as you can under the circumstances. Bye.